Hello everyone. Today I'm going to show you an example for the binary distillation systems. For this problem, we're going to separate 1,2-dichloroethane from 1,12-trichloroethane. The feed molar flow rate is 100 kmol per hour and 60% of the feed is dichloroethane. Operation is running at 1 atm and the column has a total condenser and a kettle type reboiler. It is suggested in the problem statement to use a Pang-Robinson VLE package, and we also know that the feed is 100% vapor at 1 atm. And we also know that the reflux ratio, or the ratio of L over D, is equal to 2, and we have to choose a distillate rate based on calculations which satisfy the mass balance calculations, and also we have to pick a reasonable number of stages and a reasonable feed stage. And it is suggested to try 21 as the total number of stages and 9 as the feed stage. There is one more important thing, that we want a distillate product that is 92% dichloroethane and a bottom that is 8% dichloroethane. So this is the difference between the previous problem and this problem. So we have a goal here and we have to reach that. So let's start our simulation by clicking new and just double clicking on the new case. And okay, as usual, first two things we have to do is to add our components and choose our fluid package. As I told you before, we have two components. It's a binary system, so the system is really slow. So just click add. The first one is 1,2-dichloroethane. Okay, got it. And the second component is 1,1,2-trichloroethane. So you can see our components here. We have a binary system. So let's go select the fluid package. As suggested in the problem, we are going to choose Pang-Robinson. And you can see the green bar here. So let's enter the simulation. As usual, first thing we have to do is to add a material stream as our feed stream, and let's input the available information in the problem statement for the feed stream. So let's call it feed. It is 100% vapor and the pressure is 1 atm. And the molar flow rate is 100 kmol per hour. And let's go to the compositions, and we know that 60% of the feed is dichloroethane, so the rest should be trichloroethane since it's a binary system, and the summation of the mole fractions should be equal to 1. So just click OK, and you can see here the green bar, so we have enough information for our feed stream. The next step is to add a distillation column. So let's go back to the let's go back to the model palette, and let me just make it bigger. So click on the separator tab, and this time instead of a simple separator, we're going to choose a distillation column, which is the first vessel from the left in the second column. So bring it to the simulation environment, and let's double click on that to complete the given information. When you double click on the distillation column, you can see a window which is called Distillation Column Input Expert, and we need to put a value for the total stages, choose the inlet feed stage, choose 2 energy streams for condenser and reboiler, choose a bottom product and overhead product, and also we have to choose the type of our condenser. So let's start with the problem statement suggestion, which was 21 as the total number of stages. Our feed stream is our inlet, and it should be entered at the 9th stage based on the problem statement suggestion. QC as the condenser energy stream, we have total condenser based on the problem. L or any other names as our overhead liquid outlet, and Q R as the reboiler energy stream, and B as our bottom product. So after entering this information, just click next. In this window, we have to choose the type of our reboiler. And since it is mentioned that we have a kettle type reboiler and we don't have a heater or heat exchanger, we stick with this regular HYSYS reboiler and just click next. So it was mentioned that the operation is running at 1 atm, so the pressure for both condenser and reboiler should be equal to 1 atm. And also, since it wasn't mentioned that we have any pressure drop, just leave these numbers for the pressure drop to be equal to 0 and click next. In this page, we have to put an estimation for the temperature, and we don't have any information about the temperatures in the problem statement, so just click next. And we know that the reflux ratio, or L over D ratio, equals to 2, and we have to calculate a correct value for the distillate rate based on the mass balances equations. So we will do it at the next step, so just click done. And you'll see this window open for the column T, which is our distillation column. These are the new information that we have put in for the distillation column. So let's go to the monitor tab under the design and check what are the available information. So as I mentioned before, we have to calculate the appropriate amount for the distillate rate. After doing calculation, you'll see that this should be equal to 61.90 kmol per hour. After entering that number, you can hit the run, and you see that the column is converged, and you can check the results. The most important thing that we have to check is the concentrations at bottom and distillate, because we have a target and we have to reach that. So as always, just click on the worksheet tab and let's go check the compositions. So the composition, the mole fraction for the dichloroethane should be higher than 92%, which is 95, and okay, and the molar fraction for trichloroethane in bottom should be higher than 92%, and it's 97. So we did a good job, and the values that we got, it means that there are even purer that are requirement. So let's go check the K values, which is asked in a part of the problem statement, to check the K values after converging your distillation column. For doing that, go to the Design tab and click on, go to the Performance tab and click on Plots. You can generate any kind of plots here. It will be a tray by tray properties, and you can compare, for example, the K values at the feed stage, the bottom stage, and the top stage. So click on K values and hit the Q graph button, and that will give you the K values based on for each stage through your entire distillation column. And we know that the feed stage is the 9-1, and we have the K values for these two components. And you can generate any other kinds of figure here, and also, as you've learned before, you can add a equilibrium unit to generate equilibrium plots for the system. Under the Alt tab, scroll down and add this equilibrium unit, and let's generate the equilibrium plot for these two components running, and the operation is running at 1 ATM as we mentioned before. So these are also the binary plots, equilibrium plots for this system. So one of the main questions was to know about the total number of stages in the feed stage. We did the simulation and finish it and reach the desired compositions in the distillate in the bottom. And we are going to learn how to obtain the modify this and obtain the optimum number of stages in the feed stage in the next video, which is about using the shortcut column. Thank you, and let me know if you have any questions about running a distillation column for a binary system.